All right, everyone here? If you're not here, say so. All right. Okay. So welcome to Graduate Algorithms. I always start this class by showing these two people. These are maybe two of the earliest computer scientists, arguably, and ask who they are. Okay. So does anyone know who the lady on the left is? Yeah, in the back. All right, that's Ada Lovelace. Okay. So I don't know if you guys heard of this guy named Babbage. He was trying to make like a mechanical calculator, I think, to figure out some logarithm tables. But roughly, she seemed to have been acquainted with this guy, Charles Babbage, and was kind of thinking up like algorithm to solve various like geometric problems and stuff. And by algorithms, I just mean like step-by-step mechanical procedures. At that time, nothing close to a computer, nothing close to a general computer uh, existed. I think this is even before any punch cards. Okay, so, but still, she was sort of taking interest in this idea of like, oh, can you actually follow a discrete sequence of steps and do something, right? And this sort of mechanical, computational point of view before computer existed. Okay, you guys maybe know who the person on the right is. Who's the person on the right? All right, I heard some murmurs, but just say it louder. All right, so that's Alan Turing, right? Star of that movie. I forget the name. Um, okay, so Alan Turing was really kind of brought up as a mathematician. Back then, you didn't have a computer scientist, and a really clever guy. He was very interested in this problem, really posed as a mathematical, logical question, which was, can anything be computed? Okay, at some level, can you always follow kind of a sequence of logical steps to come to a conclusion? Okay, and he showed that there in fact are problems that are not computable, of course, under a very technical definition of computable. His answer is very clever. Okay, so one thing that is not computable is you're given as input a program and have to decide if it always terminates on all inputs. Okay, so at some level, debugging your program of bugs, he showed you can't actually have an algorithm that fully computes this. What was maybe actually the real legacy of that paper? I mean, of course, this is a big, important logical question. He wasn't the only person to answer the question. But to answer the question, he actually, on paper, sort of designed sort of an abstract machine inspired by a typewriter. We call it a Turing machine now. But it's very much was the predecessor for modern computer design. So however many years later, when von Neumann is trying to build a computer, he's actually reading Alan Turing's highly theoretical paper and reading this back end about this sort of imagined computational device, which was at the time just a gadget to complete his proof. Okay, so these are two people thinking about computation before computers really existed. All right, okay, so that's fun. All right, so here's the kind of standard boring slide. Okay, so right, so this is Graduate Algorithms. The most important thing is the course website is oh, that was from last class. Okay. All right, is fundamentalalgorithms.com. There you're going to find a very large PDF, which we'll use to contain all the information. That includes lecture notes, homework assignments, syllabus. Please check out the syllabus, schedule, and all that. I won't really use Brightspace. The only thing you'll find on Brightspace is a link to this. Okay. So please read the syllabus. I'll have some time at the beginning of the class to answer various questions. Maybe some things I should highlight. We have two very good TAs, two TAs that are enthusiastic about algorithms. Richard is here, and I don't think Xinyu is, but that's fine. You'll meet her. There's two midterms and a final, roughly spaced out to divide the class into thirds. We basically have weekly homeworks, but we'll skip a week if there's a midterm and stuff like that. We have a lot of policies to try to make things more lenient. For example, we'll always drop the lowest 20% of your homework kind of word problem scores. So if we just, however many problems we do, n just do n divided by 5, that many problems will be dropped at the end. But that's also partly to catch up like all those like little weird exceptions, like I don't know, you missed the bus or something, so you couldn't do your homework all week. I don't know. All right, so that's partly to catch all these little things that aren't like actually, you know, that don't come with like some formal note from the dean of students or something like that. All right, so that's sort of a catch-all. We also have a unique late policy. You can always submit your homework, I think up to 4 days late this year, and we will just simply take off like 35%, so you can still get 65% of the total points. The reason this is kind of funny is that we're also going to put out the solutions the day after you submit the homework, so you can actually look at the solutions, decide to change your mind, and redo it. Okay, so there's no reason to get less than 65% on your homework grade, although every year some determined students surprise me. Okay. All right, but anyway, so check that out, and we'll have some time at the beginning of next class to answer more questions in detail. Hopefully it's pretty thorough, because I roughly use the same syllabus every year. That's also a mistake. Okay, I reuse slides. Okay, all right, on to the fun stuff. Okay, so part one of the class, I want to convince you that you already know quite a lot about theoretical computer science. So I'll start with two kind of simple examples that everyone's very familiar with. All right. Okay, so let's start with counting. We all know how to count, right? So I'm going to count to 10, right? How do I do that? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, can anyone do better than 10? All right, how are you going to do better than 10? Okay, yes, okay, so here's 11, 12, 13, 14, 15, 16, 17, 18, 19. So at this point, there should be no redundancy with anything I've done before. But we can do lots of like weird things, right? All sorts of different combinations. There's some that I shouldn't do in class, etc. Right? So sure, we can do finger counting like cavemen, or you can think of your 10 fingers as bits, right? You have 10 bits. So in fact, how high can you count with some practice? 2 to the power of 9? Well, if you had 9 fingers, it's probably the best you could do. 2 to the power of 10? Okay, well, how do you do 0? Okay, and how do you do 2 to the 10? What's 10 ones in binary? It's 1023. Okay, you could do 1024 if you like winked, maybe threw an I in there, you got one more bit, etc. Okay, all right. So very, very simple. Of course, you guys know this very well, right? Here's 2 different ways to represent the number 23. I think we can all agree that the right-hand side is much more efficient than the left-hand side. Okay, nobody really knows if there's actually 23 lines on the left. People get about halfway through and then they lose track. Okay, so decimal notation. If you had k digits, how many numbers can you express? Sorry. K power 10? I don't. So you have the numbers 0 through 9, right? Those are your digits. And if you have k digits, how many numbers can you express? Distinct numbers. Someone needs to be bold and say it loud and clear, or we'll be stuck on this point. 10 power k, okay, 10 to the k, right? 10 choices for the first one, 10 choices for the second one, so 10 times 10 times 10, okay. Right? Okay, this is kind of obvious. You guys already know this, but it's significant, right? Because this represents combinatorial explosion, right? Each digit, which is just writing one more character, is multiplying the number of possibilities by a factor of 10, right? So very few digits can express very large numbers. Okay, let's look at the opposite. This is, again, something that you guys probably know very well. This was a game that my elementary school teachers would play when I was in like 2nd or 3rd grade. It was always like right before recess, Or I feel like it was after recess started and we really wanted to get out of the classroom. Anyway, that's besides the point. But the teacher would say, okay, I'm thinking of a number between 1 and 100. And then we would like guess a number, and the teacher would say, oh, the number I have in mind is either over or under the guess. And then we guess again until we get it right. I don't know. Have you guys played this game before? It's like a big deal in American elementary schools. So, okay. All right, so I'm thinking of a number between 1 and 100, and I'm going to let you guys guess. So don't be shy and shout out 50. Okay, 50. Over. Sorry? Okay. 75. Over. Be loud and clear. Sorry? 87. Under. Still under. It was under 87, by the way. 80. Let's go over. Over. Under. Over. Okay, good. You guys got it. All right, so it took you guys 9 guesses. I think that's historical worst. I do this every year. Okay. Okay, but you guys got the game. All right, so what's the slow way, but maybe a sure way to win this game is to loop from 1 to 100. Guess 1, guess 2, guess 3, guess 4, right? In the worst case, it'll be 100 and it'll take you a while to get there. Okay, so but the fast way, which you guys largely got, minus some exceptions, right, is to start at 50, right? Obviously, I'm not going to pick 50, right, because I know you're going to guess 50, right? So you're not picking 50 because you think the secret number is 50. You're picking 50 because it reduces the number of possibilities in half. You're picking 50 because it's the median of the range. Whether I said over or under. If I said under, now you're between 1 and 49. If I said over, you're between 51 and 100, right? So what you guys all understand is that the goal is not actually to guess the number. The goal is to eliminate possibilities. The goal is to deduce the number, not guess it. Okay? So, all right, so if I'm going from 100 down to the final guess, right? How many rounds will this take? Or you can describe it as a function, or functionally, so to speak. Log base 2n, what is n? 100, okay? Which is about 6.67. That means that if you halve it 6 times, you'll get some number less than 2, which must be 1. Okay, so 6 rounds suffice. Okay, so 6 rounds is really all you need. You guys took 9. Luckily, all the tests will be curved. Okay. All right, so you guys already know this, but this is really important, right? We have 2 functions at play here. One is the exponential function, right? 2 to the n. I'm taking 2, multiplying it n times, right? Every single number doubles. On the other hand, I have a logarithm, right? Logarithm base 2 of n. Okay? So by definition, that's whatever number satisfies 2 to the log 2 of n is equal to n. You could think of that as how many times I have to take 2 and multiply it by itself, starting from 1 actually, 1 times 2 times 2 times 2, to get up to n. All right, you can have different bases. There's log base e. E is the Euler constant. That's sometimes called the natural log. Log base 10 was like, I remember used in my physics classes in high school. In general, you can have log base b of n for any value of b greater than 1. Okay, it'll just be how many times you have to multiply by b until you get up to n. Okay, these are all roughly the same up to a constant. Okay, so to try to exaggerate this, I try to think of, okay, what's the biggest number, natural number out there? So I thought, okay, how many atoms are in the universe? I didn't know, so I asked Google, and I trust Google. If you can't trust Google, then I don't know how you'll solve the homework. Okay, so apparently there's 10 to the 82 or so atoms in the universe. This is called the Eddington number. Eddington is a very interesting guy who verified one of Einstein's theories, among other things. I think he also invented what's called the H-index on Google Scholar. Anyway, and I think he was a terrific biker or something. Okay. So Eddington. Eddington's number is the estimate on the number of atoms in the universe. So if I took the logarithm of the number of atoms in the universe, okay, so 10 to the 82, we can agree that's a pretty big number. 82 zeros, I'm not going to write them out. Okay. Log base 2 of 10 to the 82. Okay. And as we know, the exponent drops out of the logs, right? There's these basic math rules. Okay. And log base 2 of 10, anyone have an estimate for what it is? Yeah, why 3 point something? Yeah, so 2 to the power 3 is 8, 2 to the power 4 is 16, so there's got to be something in between. Luckily, I double-checked ahead of time, so I guess it's around 3.32. If you multiply that together, anyone really quick? $246 or something? $256? Okay, I wrote something down. I got 272, so it's hard to multiply. Okay. All right. Okay, so 10 to the 82 is literally an astronomically large number. 2 to the 272 is a number you can now count to on your fingers. Okay. All right, to try to exaggerate the effect of a logarithm even more, what happens if you take the logarithm twice? Okay. So then you get, I plug in log base 2 of 272.4. That's one log of the atoms. Okay. And what is this roughly? About 8. Bigger or smaller? Because yeah, okay, so 256 is 2 to the 8, 2 to the 9 is 512. It's got to be something in between. I guess that's all I wrote. Okay, it's 8 point something. Okay. All right, so if you take the logarithm twice of the Eddington number, which is the largest number I can think of, you're now down to 8, which is quite modest, and you could have counted on your fingers before the lecture. Okay. All right, so the point is, logarithms of big numbers drop very rapidly. Exponentials would go in the reverse direction. If you take 8, you did 2 to the 8, you get, I guess, 2 to the 72-ish, 2 to the 6. If you do 2 to the 8, you get very close to the number of atoms in the universe. All right, good. All right, so I'll suggest at a high level, a very reductive level, but nonetheless, that a lot of theoretical computer science is about distinguishing these two regimes, 2 to the n and log base 2 of n, okay? 2 to the n represents some kind of combinatorial explosion. You're looking at like n bits of information, but there's 2 to the n possibilities, okay? And we don't know how to navigate it. Okay? And log base 2 of n, like the over-under game, right? That comes from binary search. Algorithms roughly called binary search. This denotes, for example, a lot of structure in the problem, right? Because you have n bits of information, but you have some strategy where you can really cut things down, right? You have n numbers, right? And you're trying to find one, but they're sorted, right? So when you do binary search, you can actually eliminate half of them in each round. So when you're getting a log base 2 of n, what that really denotes is a lot of structure underlying your n bits of information. Okay, so when you get something like logarithm, that means you really understand what's going on. You can really dissect the problem. You can really pull out information quickly. When you have 2 to the n, oh, you're in a world of hurt. Okay, that means like you're looking at n things and they're all interacting with each other in weird ways. So you get weird combinations. You can't make heads or tails of it. So you're completely lost. At some level, trying to distinguish one from the other is what the class is all about. All right, so you guys knew that. All right, second part of the lecture, pretty standard topic, sorting. I'm sure you guys have probably seen it all before, but not everyone has, and I can't skip it in case someone hasn't. Okay. So, sorting. The input is a list of n numbers. Okay, here I think are 11 numbers. Okay, and the goal is to sort them in increasing order, or technically non-decreasing order. Okay, so ties are fine. Okay, so just to make sure we're on the same page, I'm going to ask you guys to sort this set of numbers and tell me one at a time what number comes first, what number comes second, and so forth. Make sense? All right, what's the first number? 1. What's the second number? 2. What's the third number? 4. Fourth number? 5. Then there's a sneaky second 7. Then, oh, it's getting tricky. You guys are getting inconsistent. And then, can't fool them twice. And then, 11. Okay, so just listing the numbers in sorted order. I guess, I don't know if this is a great visual metaphor, but if you think of like the numbers kind of originally along the lines and they're going up and down, I drew it as a continuous wave, but it could be more chaotic than that. Once you sort them, you're going to have something that looks nice and smooth and increasing. Okay, once the numbers are rearranged. All right. Okay, so we all know what sorting is. All right, how do we sort numbers, right? Or at least how do I sort numbers? I'm not a very good computer. Okay, so if you're looking at a list of numbers, right, and you're told to sort it, what's your first natural step? What do you think to yourself? Sorry? Smallest number. What number comes first is, I think, the most natural thought, right? And so, as you guys notice, okay, that's 1, right? And you write it down. And it would be easier, and it would have made it easier earlier if I had marked them off as we did them. So let's mark it off, okay? All right, what's the second step of the human sort algorithm? What do you ask yourself? What comes second, right? All right, what comes second? And then what you do is you scan down the list looking for the second smallest number. You already know that 1 was taken, so you kind of skip that, especially if you mark it, that makes it easier. And then you recognize, okay, 2 is the smallest, and you write down 2. Okay, simple algorithm, and probably the way we've always sorted all our lives. Okay, so, all right, so the algorithm at a high level is kind of building a sorted list one at a time from beginning to end. Each time I have to go through the whole list to find the next unused smallest number. Okay. All right, how long is this going to take roughly? All right, there's some kind of outer loop, and then there's some work in the loop. Maybe another loop. Okay, so how many outer iterations are in this algorithm? N, yeah, oh, sorry, on an input of size n. Okay, there's n iterations. Okay, and really the bulk of the work in a single iteration is scanning the thing all the way through. Okay, so how many items do I have to scan each iteration? N. Okay, so roughly there's n iterations. Each time I do n units of work or so. So that comes up to roughly how long? N squared. Okay, fine. So it takes us n squared time as people to sort a list. Okay. Now it's very vague what I mean by time here. We can make it somewhat more formal by introducing big O notation. I believe most of you have seen this to some extent before. Okay. So big O notation, when I say big O of n squared, what I'm saying is that there exists some constants, capital N and C, okay? So for all inputs, there should be some constant. It could be a big constant, it could be 1,000 or something, but it needs to be independent of the input size. For all input sizes greater than this capital N, the algorithm terminates in at most Cn squared steps. Okay. So, okay, I'm not worried too much about like problems of size 1, 2, 3, 4, and 5. In general, you could probably brute force anything of that size anyway. I'm really interested in the large inputs. I'm really interested in how the running time grows with the input size, right? Because once I sort of write big O of n squared, it draws a lot of attention to the n squared and the functional relationship with the input size. Okay. All right, but there's something, somewhat unsatisfying, I think, about this definition, and that's what the hell is a step, right? It's not really clear what a step is actually on a computer, on your code that you actually code and you run, right? It's going to vary on your computer. It might vary on the language. There might be a garbage collector in the background. It might depend on whether the sun is shooting photons off your RAM and flipping bits randomly, right? I don't know if you guys have taken a compiler class, but what we write down as one step often breaks down to many more low-level steps, right? And then at the bottom, then you have to deal with like things getting swapped in and out of the register and various levels of cache and all these kinds of things, right? And the moment you think you understand one system, a year passes, a new iPhone comes out, and you're already outdated, right? So these things are also changing all the time, okay? But, the point is that we're allowing for this extra constant C to be in front. And I'm not really concerned with the constant. The point being that, these low-level details exist, but they're only going to affect the constant. Okay, maybe the assembly language changes, the compiler changes or something, so it's a little bit more efficient now. Maybe that constant goes down like a little bit. Okay, but it's still asymptotically going to grow like n squared. Okay, the constant goes down. Okay, and all these low-level details that make you, kind of distract you from the essence of the problem, they only affect the constant, and we're not going to worry about the constant. Okay. All right, so the real point, the moral point of the big O notation is to hide that constant and in that sense, hide all of the domain-dependent details, the machine-dependent details, so that we can develop a more general theory of algorithms that's independent of the exact computer you're running on. Right? So we can solve problems somewhat more abstractly and not worry about whose laptop it's going to run on. Okay, that's the point. Okay, all right, so much for big O notation. Okay, so human sort, also known as selection sort, takes n squared time. Okay, the question is, can we do better? I know that most of you know the answer to this, but still kind of an interesting question, taken from first principles, right? Because if you think about what n squared is, okay, n squared in a sense is a very natural running time because you have n numbers, and if you compared all the numbers to each other, you get n squared comparisons, right? So you can think of n squared as really saying, oh, basically each number is being compared to every other number, and that's where n squared comes from. Okay. Right. So when I say, can you do better than n squared, we're kind of asking an interesting conceptual question, which is, can we sort all the numbers without comparing every pair of numbers? Okay, is it really necessary to execute all the comparisons, which a priori, if you hadn't studied for coding interviews and various things, it's kind of an interesting question. Okay, so here's maybe a different perspective, or a perspective that one can often take when trying to improve an algorithm, which is to consider the related problem of verifying a correct solution, verifying if a solution is correct. Okay, so play with me. Suppose I give you an array of numbers that's supposedly sorted. It's supposed to be sorted. Okay, and so the question is, how long does it take to verify that this array is sorted? Okay, so you don't have to actually sort it if it's not sorted. You just have to tell me if it's sorted or not. It's potentially easier. How fast can you do that? Okay, how? Okay. So it's sorted. I don't have to actually compare all pairs of numbers. So if I know that A1 is at most A2, A2 is at most A3, A3 is at most A4, right? All the way down the line. Then because of transitivity, if A1 is less than equal to A2 and A2 is less than equal to A3, A1 is less than equal to A3, right? You actually have verified all pairs, right? Because there's a little bit extra structure when it comes to sorting. Okay, so that's a linear time algorithm. There's not much to it. Okay. All right. So we know how to sort in n-squared time. We know how to verify a sort in n time. Okay. So that's saying, oh, okay, there might be something in the middle. If we didn't have a better if our best verification was n-squared or something, that would be a little discouraging. But right now there's a gap. Okay. All right. Can we do better? All right. What are other ways to try to generate algorithmic ideas? Well, one way is to consider special cases. Okay, so let me give you an easier case of the problem. So instead of like a completely mumbo jumbo input, suppose I told you that the first half and the second half of the input was already sorted separately from each other. Okay, so the first n over 2 are sorted, the second n over 2 are sorted, but there could be things in the second half that are smaller than things in the first half. Okay, all right. How fast can you produce a sorted list? Okay, I heard O then. How would you try to do it? Okay, so let's think about, for example, what human sort would do, right? Human sort would first look for the smallest number out of the whole array, right? But if I knew that the input was structured in this fashion and I wanted to find the smallest number, I don't have to look at the whole array, right? I only have to look where? At the beginning of each of those two lists, right? I only have to look, here and here. And I compare those two numbers, maybe this one's smaller, I write that one down, right? And now when I want to look for the second smallest number, where do I look? I only have to look at the next slot of the first and still look at the first spot in that second list. And maybe it's this number and I write this down, okay? If I have two sorted lists and I want to actually just run human sort, I only have to look at the front of each list to keep plucking off the next smallest number. Okay. All right, so I know some people murmured this. This is called merging two lists. The full pseudocode looks more complicated than it really is. It's exactly as I described. You're just going to allocate first a big enough space to fit both the lists, and then you're just going to go through and keep taking the first one. The total running time is going to be linear in your total input size because each time you're advancing that pointer down the list until you get to the end. Okay. All right. Okay, so that's called merging. It's going to take linear time. It's going to take two sorted lists and output one sorted list. Okay. So this merging inspires sort of maybe a divide and conquer approach. That's not really quite fully satisfied yet, right? But okay. I right now know that I can take two sorted lists and combine them very efficiently. Okay. So maybe here's an approach. Given some large input, I'll divide it in half. I'll sort the first half, I'll sort the second half, and I'll get two sorted lists, and I'll combine them. Sounds reasonable, right? The only weird thing about this is how do I sort the first half and the second half when the original question is how to sort a list, right? Seems not kosher. You ask me how to sort a list, and I tell you, well, you sort the first half and you sort the second half, and then it's easy, right? It's hardly a satisfying answer. Okay, so how do I sort the first and second half? Yeah. Keep on dividing, keep on dividing. Yes, but I want to say it more concisely and more Well, it's grungy, right? To imagine dividing things in half and half and half and half, right? It's a more elegant way to kind of express this. Yeah, so how do we sort the first half? Oh, you say sort the first half of the first half. Okay, so if I did that, right, and I kind of wrote it out, and I said, okay, this means that one, I sort the first half of the first half of first half, okay, and then I said, okay, and then you also on step 2, you're going to sort the second half of the first half, right? Okay, so now I have taken my 3-line code, I've made it a 4-line code. I replaced that first line by, it used to say sort the first half. Now I'm going to say sort the first half of the first half, then sort the first half of the second half, or second half of the first half, and then sort the second half. Okay, great, but I'm going to ask you the same question. How do you sort the first half of the first half? Yeah, okay, the word I'm looking for is recursively. Okay, this is the magic word. Okay, when I tell you that I'm going to sort the first half and sort the second half and then combine it, I'm not cheating. Okay, that's actually a satisfying answer as long as we sort of double check some formalities. Okay, so we're going to sort the first half recursively. I'll explain that in a moment. We're going to sort the second half recursively. That means I'm going to use the same algorithm on itself, and then I'm going to combine the lists. Right? It feels like cheating, but it's not. And it's obviously very simple if you're comfortable with it. Okay, so how do we design a recursive algorithm? This is important, and I'm going to be very picky about this. Okay, on all the homeworks and stuff. Okay, so say I want to make a recursive algorithm. The first and most important step is to declare what your algorithm does. Okay, write the name, write the input, what goes in, what comes out. Okay, I'm going to call this algorithm merge sort because that's what it's going to be called. It takes as input an array of comparable numbers, and it outputs an array of those same numbers in sorted order. Okay, it's really important to write this out. Why is it important? Okay, so we declare the input, the output. First of all, just in real life, nobody wants to read your code and try to figure out what the input and output is. Okay, so that's just good practice so that you have friends at work. All right, but more importantly, okay, when we write this sentence, we're setting up a contract, so to speak, that the algorithm must fulfill. That's going to make it a little bit easier to implement, right? Now you've made very clear to yourself what you need to do. Fine. But then most important of all, when you start doing recursion, right? I say, okay, I'm going to sort the first half using this algorithm. Well, what happens in the first half? It's going to do exactly what the sentence says. Okay, why? Okay, so that sentence is also going to serve as your induction hypothesis in a proof of correctness. Okay, at a high level, you're going to prove that for all n, merge sort works on inputs of size n by induction on n. Okay, so you're going to double check 1, double check 2. And knowing that you can do anything smaller than n, can it do n? Okay, induction is not cheating, it's correct. Okay, so when you write this sentence, you're also setting up the induction hypothesis and really explaining why the algorithm is correct, why your recursion is actually a proper recursion, it's not cheating. If you don't have it, you are cheating. Okay, and you could make mistakes. All right, so once you write down that sentence, then you implement it. And this part is relatively not so bad. Okay, this is the stuff you guys probably already knew how to do. Given a sentence, turn it into code. The harder part is finding the right sentence. Okay, so let me just point out some basic things about this code. You know, the first step is addressing a base case. Okay. Oh, if there's 1 or 0 elements, it's already sorted, right? So we just return the same list, same array. No big deal. Okay. And then otherwise, right? You know, I split the input by, m is like the middle point, and then I look at the first half and the second half, and I call merge sort on the first half and merge sort on the second half. The same algorithm on the first and second half, right? And I'm okay with this. I'm comfortable with this because, right, I know that those subcalls are going to satisfy the recursive spec by induction on n, by induction on the number of elements. Okay, so you have to double check and make sure your arrays really are smaller, right? So check your base cases carefully. Double check it works for n equals 2, n equals 3, and it's really getting smaller. Because if you have if you round up instead of round down or something weird, you sometimes keep sending in the same size input and get infinite loop. Okay, right? But I know that recursion is okay by induction on n, and I know in particular it's going to do exactly that sentence. So I'm not thinking about that crazy dividing by half, dividing by half, dividing by half, dividing by half. Nobody would do that, right? That's too much work. I'm just saying, oh, it's going to do that sentence. I'm cool with that. Okay, and I don't think any further than that. I'm not dividing the first half of the first half of the first half. Okay, and then we merge them together, and that's pretty simple. All right, okay, so recursive spec, implement the spec, and how do you prove correctness? Really, once you have the code there, and you have the sentence there, you just have to write a short thing explaining why the algorithm satisfies the recursive spec for and by induction on n. Next class, we'll talk a lot more about induction. Okay, you check the base cases, and you prove n, assuming it works for everything smaller than n. Okay, it's almost boilerplate if you set it up correctly. For most problems, sometimes it's trickier, and you have to make a few more comments. But okay, if you get that sentence set up, your life is easy. If you get that sentence set up, you basically pass the class. Okay. All right. For what it's worth, if you wanted to think about it as dividing up and all this stuff, and you wanted to see the full landscape, it'll look something like this. Okay. Here you can sort of see the divide and conquer sort of thing going on, right? The beginning, we keep dividing in half until we get to very small problem sizes, and then base cases, and then we start coalescing them together with merges. Took me a long time to draw that picture. All right. Okay. All right. So, all right, let's analyze the running time. So we've basically established correctness, right? Correctness follows by proof of induction based on the recursive spec. The other part of our analysis is going to be about how fast does it take. Remember, our goal is to beat n squared. Okay. All right. So what we do is we model these things mathematically. Okay. So I make up my own equations and stuff to help me understand the situation. So I'm making up, okay, I'm going to say that T of n is going to be an upper bound on the running time for any input of size n, or size at most n. Okay, I've defined T of n, time of n, I guess. Okay, but that's just my imagination. And I'm going to start trying to formulate what T of n might look like, right? So typically we start small, we just do the base cases, right? So T of 1 or T of 0, how long does it take on an input of size 1 or input of size 0? Yeah, constant, just 1 is fine. We'll put a big O around whatever calculations we do at the end, so I don't really have to distinguish 1 from 10 at this stage. Okay. The more interesting stage, or more interesting part is trying to model T of n for kind of a generically larger n. Right, and that's really what obviously you knew what T1 and T0 is equal to. All right, so how do I model T of n? How can I express it? So what does the algorithm do on input of size n? Well, it makes, okay, so let's see. So it's going to, for example, so divides the input and it finds the median point, right? Does some calculation that takes constant time. And then it sends the first half of the array to some kind of subcall, right? And how long does that subcall take? So it's going to be roughly n over 2 elements sent to that subcall. And how long does the subcall take? T of n over 2. So we can use the same kind of trick. So, okay, formally, it might be like rounding up n over 2 kind of thing, right? And I do another subcall with the remaining elements. How long does that take? So it should be the remaining elements, like n minus n over 2. I'm just being detailed for a moment. We'll get rid of some of these details in a moment. Okay? And what else does the algorithm do? It merges things together. How long does that take? n, or big O of n, or something like that, plus n. Okay, so that's roughly, how long it takes. I've already written this, so just like that. You don't have to put the big O of n there. I just did, but it's not really an issue. Okay, fine. All right, so when you're encountering a situation where it's like, oh, this sort of ceiling of n over 2 is obviously annoying and besides the point, you're allowed to just simplify this and say, okay, this is 2tn over 2. I'm only off by 1. Okay. This is obviously correct for n being any power of 2. Okay. And I promise you this is correct. There's a couple of different ways to argue it, but you just have to do some calculations, so it's in the notes. Okay, but when you're in this situation where you're looking at like, oh, is it exactly n over 2, or is it n over 2 plus 1, or n over 2 plus 2, you can just write n over 2. It's actually going to come out, it's going to end up the difference is going to hide in the big O notation at the end anyway. Okay, so I give a couple of different arguments in the notes. They're all formally correct, of course, but it's not super exciting, so I won't do it here. Okay, but also morally, this is probably what you have in mind, right? It's 2 times half the input size plus big O of n. Okay. All right, so I've now modeled recursively what the running time is. Modeling is always basically the hardest part. Okay. Now let's try to make some sense of this. And we're going to do something called a recursion tree. This is how we're always going to analyze divide and conquer algorithms. No master theorem stuff allowed. Okay. All right. So what's a recursion tree? So what's the idea? So I'm going to draw a tree where every node represents a subproblem. Okay. So the root represents the original problem with size n. It branches off into 2 subproblems of size n over 2. Each of those branches into problems of size n over 4. Okay. So I kind of draw the first few layers of a tree just to get some sense. Okay. And I draw in the middle the input size. Okay. This one is, maybe a little symmetric, so you might think this is boring, but other situations will be more complicated. Okay. Okay. So I'm gradually visualizing and getting some sense, right, for what the recursive structure of the algorithm, right? This reflects quite a lot of the structure. Okay. Now, what I'm going to do is I'm going to look at, say, that top node and say, excluding the recursive calls, what's the total amount of work for that problem? Okay, the running time for that problem, excluding the recursive calls. Right? There's some running time deferred to subcalls plus the time done at that subproblem, right? So for that problem of size n, how much work do we have to do besides the subcalls? Not constant, because we did more work than constant. N, because we merged. Okay, so I did roughly n work. Okay, now let's go to the next problem. N over 2, right? How much work did I do for one of those n over 2 problems? Just one of them. I think you guys are saying it, but it's too quiet. N over 2 is again linear, right? N over 2. And in that third row for problems of size n over 4, how much work am I doing per subproblem? N over 4. Okay. All right, fine. Not a big deal, right? I'm just kind of annotating and keeping track of how much work I'm kind of doing with each subproblem, kind of for that subproblem, excluding subcalls, right? Now here's the cool part. I'm going to add up all the rows. Okay, so let's look at the first row. What's the total amount of work for all the nodes at the top row? And it's just one thing of size n. Okay, what about the second row? N, because you have 2 times n over 2. Okay, what about the third row? Again, it's n. Okay, it's going to be n all the way down. Okay, presumably you're comfortable with this continuing on. All right, so much for that. Now I want to add all these things up, right? The question is, how many n's are there? That's the same as asking, how tall is this tree? How tall is this tree? Log n, log base 2 of n to be exact, but the base doesn't really matter. Okay, log n is the height. Okay, so when I add all these up, it's n times log n and log n. Okay, running time is n log n. Okay, and so what's great about this is it's childish, but you can really see like where the running time of the algorithm's coming from, right? This sort of tells you something about the algorithm. It's not just some kind of calculator. Okay, there'll be other situations next week when we do more sophisticated divide and conquer, where the numbers inside aren't so nice and symmetric, like n over 2 and stuff. You might get like n over 3, n over 5. It might be mixed. Okay, but the recursion tree will still work. Okay, for those who are aware of the master's theorem, you can use the recursion tree to prove the master's theorem, so to speak. But don't use the master's theorem. Okay, it's also a bad name. All right. Okay, so much for recursion trees. That's sort of how you analyze divide and conquer type stuff. We'll have more examples next week. All right. Okay, so for the last part of class, I feel like we're running way ahead of schedule, but I guess you guys don't mind. We'll talk about trying to get lower bounds for sorting. Okay, so where are we? Okay, so, all right, so we just got n log n for sorting. That's better than human sort. Great, I'm sure you guys, most of you were aware of this algorithm coming in. And the natural question to ask is, can you do better? Right? It's always the question we ask on any problem we're working on, right? Or, sort of the contrapositive, is this already the best we can possibly do? Is merge sort, so to speak, optimal for this problem in terms of running time? Okay. All right, so our goal is to somehow try to prove a lower bound for all sorting algorithms. I'm not trying to prove a lower bound just for merge sort. I'm not trying to show that merge sort, like our analysis wasn't very good, right? I'm not trying to show that, oh, there's some examples where merge sort gets n log n. I'm sure we could think of some. I'm sure it won't be very tough. But I'm trying to do something more ambitious. I'm trying to argue that any sorting algorithm will need to do n log n steps. The ones I've never thought of before. The silly ones, right? Okay, so I want to somehow come up with some kind of abstract argument. I think this is arguably tougher than trying to find a good algorithm. I feel like when I'm trying to find a good algorithm for sorting, it's a very concrete problem. And I only need one good algorithm to get a good bound, right? It's a there exists kind of thing, quantifier. But here I'm trying to prove a lower bound for all possible algorithms, say for all kind of quantifier. And that just seems more challenging to me. I mean, maybe you're different. For me, if I have like a concrete problem, then I can think of clever things and focus. For doing lower bounds, you have to be more disciplined, I feel like. All right, so I'm going to try to argue that for some function f of n, some function of n, that any correct algorithm has to take, and the notation is at least big omega f of n. So what's big omega? It's just like big O, but on the lower bound side. So okay, there's some constant c and n, so that for all inputs of size at least n, it takes at least c fn time, f of n time. Okay, same concept, nothing really new. All right, so how do we go about this? Well, one thing that's really important is to actually fix a model, which is going to restrict a little bit, kind of, not too much though, all the algorithms that we're trying to worry about. So we're going to focus on what's called the comparison model. It's a very natural model, okay? So it says, okay, you're given n comparable elements, right? But you don't really know anything about the representation of the element. You don't have they're not like necessarily bit represented numbers. So all you can do in this model is take two of those elements and ask, is one bigger than the other? And you get a yes or no answer. Or you can ask if they're equal or whatever, okay? But just a few Boolean queries with yes or no answers, okay? And so rather than trying to kind of focus on the running time, I'm going to focus on the number of comparison queries that a sorting algorithm has to make, right? Because seemingly any reasonable algorithm needs to at least constant time to compare two things. So if I can show that, oh, you need to make n comparisons, then you should take at least n time. If if I show that these n log n comparisons, it should take at least n log n time for any kind of reasonable model I can think of, right? It's important to point out whenever you assume the model, the things the model excludes. So if you're looking at like integers that are 32 bits long and represented in bits, right? So you can do weird things like look at the most significant bit, least significant bit, and stuff like that, and maybe try to play games with the bits. That's excluded from this model. This model won't, I mean, a lower bound in this comparison model won't tell you anything about weird bit games you might try to play. Okay, so it's not perfect, but it covers many natural cases. Okay, so I'm going to try to get a lower bound on a number of comparisons in the comparison model. Okay. All right, so is there anything down here? No. Okay. Does anyone want to, since we have plenty of time, try to guess how to pose an argument? It's worth trying once, right? Because once I give the answer, you won't get this chance again. How might you try to begin an argument proving a lower bound on the number of comparisons of a sorting algorithm? Yeah. Okay. We're going to have to look at each number at least once. So here's where things get tricky, right? I absolutely agree intuitively. But then when you say must, I don't actually 100% know if you really must. I don't know if there's a more clever, bizarre idea out there. I kind of agree, and maybe we could formalize it, but at the moment, it's not a fully formal statement, as obvious, as completely obvious as it sounds. That also only gets us the lower bound of n, which probably we were comfortable with mostly anyway for that same reason. I would like to also do something better than n. But it's still a good idea, right? I mean, it's a good attempt. I think it's a natural attempt. Any other ideas? It's quite natural to be stumped. I wouldn't know where to start either. But it's still nice to try these things before the answer is unfurled. Can we do a proof by contradiction is roughly what you're suggesting? Sure. But to say that we need to look for a contradiction is a little bit kicking the can down the road. Yes, we're going to look for a contradiction or some kind of, logical implication. Okay. All right, so let's say the algorithm, we don't know anything about the algorithm, right? That's one thing that makes this argument so tricky. Okay? So I don't know anything about the algorithm. I'm not going to try to guess what it does. I can't assume anything. As soon as I assume something, then my argument's kind of weaker because it only applies to algorithms under this assumption. Okay? So what I do know, let's say it makes k queries. And I know the input and the output, right? So I know it takes an m elements, it makes k queries, and it outputs a list, right? I know the output of the algorithm. I'm not making any real assumptions about the algorithm, like how it comes up with a list. All I know is it makes k queries and it outputs a list. Or let's say at most k queries in the worst case. Okay, fine. So that much we know. This is roughly all we know about the algorithm, or a generic algorithm. All right, so let's put these things together. All right, so that means that whatever is output is a function of how many queries? It's not a trick question. It's okay, k. All right, this we know. Okay, however it comes up with, I don't know, but it's some transcript of k queries. And by the way, it can be adaptive, right? The second query can depend on the answer to the first, third, whatever. But at the end of the day, there's some transcript of k queries, and as a function of that, it always outputs the same list. Okay? All right. Now, every query has how many outcomes? 2. Okay. So the output is some deterministic function of at most k queries. Every query has 2 outcomes. How many things can I output? At most. How many different outputs can this algorithm make if it's making k queries? 2 to the k. Okay, so if it's only making k queries, it can only output 2 to the k different things. Because abstracting out all the complexities of the algorithm, all the intricate details, it's still a function of the k answers to the queries. Okay, anyone want to try to guess the next step? This is probably the hardest part. I mean, we've probably done the hardest part, which is really setting it up. Where's that contradiction you gave us hope about? Okay, sure. K1 to, I mean, if it's not a function of n, yeah, you're screwed. But okay, so let's say that k, I'm trying to differentiate between k is equal to n or n log n or n squared. So think of k as being already pretty large. I'm pretty comfortable with like k equals 2, 3 not being enough. Okay. How many possible outputs are there, right? So out of like, given your n elements, how many ways to reorder it, so to speak? There's n factorial possible lists, right? So those 2 to the k needs to cover n factorial possible outputs to be correct, because any one of those n factorial could be output, right? So how do I express that kind of mathematically? Or what does that tell me about the relation between k and n mathematically? Yeah? Yeah. Okay. 2 to the k is greater than n factorial just to be able to output all possible orderings of the elements. Okay? How do I, okay, obviously, this is a bound, but it's not like, it doesn't really make sense to me. I don't really know what n factorial really is. I mean, I know what the definition is, right? Okay, I want to say that k is bigger than something and that something is relatively simple so I can wrap my head around it. All right, so what do I do next mathematically? Okay, we'll take the logarithm of both sides. So k is at least the log of n factorial, where n factorial, as you guys probably know, is n times n minus 1 all down to 1. Okay, great. Yeah, it's kind of a bound. The log of n factorial is still kind of like, I mean, it's a thing, but it's kind of nonsense. I don't know what that means. I want to simplify this further. I want to kind of get rid of the factorial, so to speak, right? But it's kind of a complicated object. All right. How can I lower bound n factorial? Sorry? N factorial is less than n to the power of n. That is true. But it won't help us because I'm trying to show that k is bigger than log n factorial, which is bigger than something. That's going in the wrong direction. But it is nice and clean. I kind of understand what n to the n is. And also, I would have been able to take up the log of n to the n very easily in the next step. So n to the n is sort of nice and clean. And can you get something similar, except greater than equal to? Okay. So this is a nice trick, right? So n factorial itself seems like a big complicated number, n times n minus 1, n minus 2. It's completely garbage. But I know that at least half of these numbers, right, the first n over 2 of them, they're all at least n over 2, right? So that bracket is supposed to be the first n over 2 numbers, right? So the first n over 2 numbers, n minus 1, n minus 2, all the way down to n minus n over 2, which is n over 2, are at least n over 2. So that gives me a very lazy bound. Okay. Let's leave that up there. Okay. So k is at least log of n factorial, which is at least log of n over 2 to the n over 2. Right? Very lazy bound. None of this Stirling approximation or whatever you might find on the internet. Okay? N over 2, at least half the numbers are at least n over 2. Okay? And how does this simplify? You guys are all just giving me this. This is not helping me. Okay. N by 2, log of n by 2. That log of n over 2 is just log of n minus 1, so the over 2 doesn't really matter. Okay? So this qualifies for big omega n log n. At least n log n up to some constant. We could have made that 2, a better one if we did sharper bounds for n factorial, but who cares? All right, so what have we shown? We've shown that in this comparison only model, any correct deterministic sorting algorithm has to make big omega n log n comparisons in the worst case. Okay, so that's kind of cool, right? Because it's the quantifier is different. Any algorithm has to do it. And I think in retrospect, obviously like setting it up and getting it going like seems to come out of nowhere. But in hindsight, the argument is not necessarily that complicated. It's sort of just a counting argument, right? The number of sort of queries exponentiated has to be at least the number of possible outputs. And then after that, it's just some basic calculations, taking log of both sides, a little trick to address n factorial. Okay, so big conceptual move, but not necessarily super complicated in hindsight. That's the lower bounds I feel like are always tougher. Okay, so we have a lower bound of n log n. All right, so let me conclude. We'll finish a few minutes early, which will be the only time this semester, probably, on my record. Okay, so we've shown an upper bound of n log n and a lower bound of n log n, right? Okay, so in general, any lower bound should be less than any upper bound. If you get a lower bound that's bigger than the upper bound, then you've got issues, right? But here, in this case, right, we also have an upper bound that's at most the lower bound up to some constant. Okay, so one of these inequalities is just by definition of lower and upper bound, the first inequality. Lower bound is always smaller than upper bound, right? But we've also shown that the upper bound is, at most 100 times the lower bound. Upper bound is almost 100 times the lower bound, right? And it's these things together that actually makes both the bounds more compelling, right? Because now, can I improve n log n? No, right? At least not by more than a constant, which is out of my pay grade. Okay, so these bounds mutually certify each other to be optimal. So simultaneously, I know I have the best possible lower bound and the best possible upper bound, and we can all just go home, right? We've kind of resolved this problem completely, at least in the comparison model. And so this is important, right? Because I think we often think of, upper bounds and lower bounds as sort of in a somewhat adversarial relationship with each other. Certainly the upper bound is always above the lower bound. They seem to fight each other, right? But you could also see them as two sides of the same coin, because in particular, once they're up against each other, they actually make each other much stronger. Okay, so that's sort of I think the perspectives that we'll shed a little bit of light on in this class is, for the most part, we're often interested in upper bounds and getting things done, but sometimes studying the hard side of it, the lower bound side, can shed some light as well, right? So you get exposed a little bit to this hardness perspective throughout the class, okay? And it's not just for the sake of proving complexity results and hardness results. It's also, at some level to teach us something for the sake of understanding our upper bounds, right? I want to think of them as two sides of the same coin instead of like completely different subjects. All right, so great. So in conclusion, I guess n log n is the right answer for sorting in the comparison model, and that concludes the lecture. Okay, so all right, so thanks for coming, guys. Don't forget to look at the syllabus and come armed with questions if you have them at the beginning of next class. Thank you.